A diode is made by combining P and N materials. The surface at which these materials meet is the P-N junction. Diffusion occurs when P and N materials are joined together. Some electrons in the N material near the junction are attracted to the holes in the P material, thus leaving holes in the N material. The diffusion of electrical charges produces a potential difference in a small area near the junction. As a result, the material will conduct in one direction but not in the opposite direction. For this reason, the area in which this EMF exists is called a barrier. The positive terminal is connected to the P side and the negative terminal of the DC supply is connected to the N side of the junction. The positive terminal for the battery attracts electrons from P material, leaving excess of holes. Because electrons are drifting away from the junction, the excess holes tend to accumulate near the junction. At the same instant, electrons from the negative terminal of the battery are attracted to the less negative N material of the diode. This action overcomes the barrier at the junction and allows the electrons to move into the excess holes of P material. The result is a continuous flow of electrons in one direction. The voltage required to move the charge carries in forward bias conduction called the barrier voltage. The P side is connected to the negative and N side is connected to the positive terminals of the supply. At the same instant, a shift in electrons in the P material causes the positive holes appear further away from the junction near end of the diode, which is connected to the negative terminal of the battery. This action produces a wide barrier at the P-N junction through which the electrons cannot flow. But a small current leakage may, however, occur. The current, the forward direction increases rapidly upon reaching the forward voltage VB, which is known as the barrier potential or the junction potential. The behavior of the P-N junction is limited by the maximum forward current, as too much of current may destroy a diode due to the excess heat generation. The material. The diode is made of doped semiconductor material. This could be silicon or germanium or selenium. This is important because the cut in voltage depends upon the material the diode is made of. For example, in germanium diodes, the cut in voltage is around 0.3 volt, whereas in silicon diodes, the cut in voltage is around 0.7 volt. The diodes are printed with a type number. When this type number is referred to in the manufacturer's manual, the detailed specifications for a particular type number of the diode can be obtained. 1N is used as a prefix for semiconductors with one junction. For example, all 1N components refer to diodes because diodes have one junction. Components in the pro-electron system have 2-letter and numeral code for consumer devices. Example, BY27 and so on. 3-letter and numeral code for industrial devices. Example, ACY17 and so on. The first letter in the pro-electron type code indicates the type of semiconductor material used in making the device. The second and third letter indicates the applications of the component. The numerical after the second or third letter is the code number of its detailed voltage, current, and temperature specification. Based on their current carrying capacity, power handling capacity, diodes can be classified as low power diodes can handle power of the order of several milliwatts only. Medium power diodes can handle power of the order of several watts only. High power diodes can handle power of the order of several hundreds of watts. For checking diodes, set the meter at the diode symbol 2000. The black probe is negative, the red probe is positive. With this, we test the diode. In a diode, the ring indicates cathode, which means negative. The other side is positive, that is anode. Diode only works by forward bias. Forward bias means it gives positive to anode and negative to cathode. Connect the negative probe to cathode, positive probe to anode. Now we observe some reading. The diode is working condition. This is called forward bias. Same time, now we change the terminal leads and connect positive probe to cathode and negative probe to anode. No reading in the meter. This is reverse bias. The diode is in good condition.